Okay, so I'm really happy to do this talk because it was a lot of fun to get it prepared. So I will talk to you about state machines and nice things we can do with them. I'm Pierre Halftermeyer, I'm pre-sales engineer at Neo4j. So let me start. So what is a state machine? We also call them a finite state machine when they are finite, and they will be deterministic finite state machine. They will be deterministic in our context. Or I'll say automaton or automata plural, FSM as an acronym. What does Wikipedia says about them? So finite state machine are a mathematical model of computation. It is an abstract machine that can be exactly one of a finite number of states at any given time. The FSM can change from one state to another in response to some inputs. So we have states, we have inputs, and states change with those inputs. An FSM is so defined by a list of its states, its initial state, and the inputs that triggers each transition. So we have state and transitions. It sounds like nodes and relationship to us. So let's see it as a graph. Here is an automaton for language recognition. We'll call it the LOL language. So how does it work? I will try to find out if the word haha is recognized by my automaton. So I am in the initial state because there is the arrow, and I will read the first letter of my word, H, and that will get me to the state 1. So I have 4 states here. Then with the A, I go to the second, to the state 2, then with H to step 1, then 2 again, and with my exclamation mark, I get to the state 3. It is a terminal state, so my word is recognized by the language, is part of the language. So I have a machine that is able to recognize a word from a set, from a language. And this is the first say use case of automata. I need to put those automata in my database because we are working with Neo4j, it's a database, and I need to express them as data. There is a very straightforward mapping from my automaton to a CSV. Here, for instance, the yellow state is the first line, and the red transition is the red line, and we can see it's very easy. So when I have it in a CSV, I can ingest it. I also can ingest several automata in a single file, in a single CSV file. Here I have 3 languages, say the ABC star language, the LOL language, what we have seen, and the Python var language. A Python var is an alphanumerical string that does not begin with a number, and underscore are accepted. When I have several symbols in my transition, you can consider it's a list of admitted symbols for this transition. So we are ready to ingest. To ingest, we can use the Neo4j data importer. It's an awesome tool if you want to prototype a very fast database. So you should use it. And tada, let's see if it works. So I have an Aura instance. I have my state machines data file. My importer, I've already imported it, but if it's really easy, you draw the meta model with transition from state to state, and you can ingest your CSV from a very easy mapping. There is no code. If I do a preview, I see my automata are in the database, so I can query them. I can show you all state machines with a very easy query in my database. They are in my database. Then I can create a word to see if it works. I will create the word as a chain list of symbols. I will init my computing. I need some really straightforward code, and I'll set the language to the LOL language. This is the language against which I will check my word, and I can iterate each state and each transition with code I will explain later. If I want to iterate all state, I put it in an APOC periodic commit, and I have all my process done, and I can check if my word is part of the language, and here is accepted language. When I have it, I can build a tool to check if a word is from a language or not. For instance, from the LOL language, I can check if this word is accepted by this language, but maybe it's not by another one. It's not a valid Python variable. If I remove the exclamation mark, then it is. I can put an underscore at any place, and it will also be good. So I have something functional, a very straightforward way to build an application with a finite state machine. How do I process a word with an automaton? It's very easy. I have the chain list of my symbols and my automaton. The blue state is the current state, and this state is the first unprocessed state. And then, so first unprocessed, current state. So then, as it's an H symbol, I will trigger this transition to this step. And it's really straightforward to write this in Cypher. This is the first unprocessed, maybe the first of all of them, or the first following a processed one. This is the current state. This is the transition that contains the symbol I'm referring to. And this is the next state. When I add this, I can update my current objects really in a really easy and straightforward manner with Cypher. And I use Neodash for the front end, because it's a great tool you can use for prototyping a front end very fast. So I encourage you to use it. So we can use Automata with Neo4j, but what are they good for? And first of all, I want to share an intuition with you about control flow. Control flow in a programmation language is like structured like for loops, while loops, if then else. It enables you to control the flow of your code. And we can see that some automatas are really close to control flow. This is a while loop. While true, while I see the true event, I stay in my loop, and when false, I go to another state. And this is a if then else statement. I have a Boolean value. If it's true, I go to some terminal node. If it's false, I go to some other terminal node. So there is a mapping between automata and control flow structures, and we can build more complex control flow structures with automata than we can do with normal code. Now, what are automata good for? Some use cases. This one is from a puzzle of Advent of Code hackathon. It's bytecode parsing. You have to find packets in bytecode. Bytes are queued in the green chain list, and you have your orange automaton at the center, and you are like gluing state to sequence of bytes to find your packets. There is a link on my GitHub. You can find the code there. Then you can control the gameplay of any game with an automaton, and the automaton orchestrates the gameplay. It's like the referee of the game, and it can trigger any event from where you are in your gameplay. So this is a dice game with 2 players, and you can see there is code in a state. A code is triggered and is inside the state. It's like meta programmation with graph. And I will use this strategy later to show you something. This is an AI problem. I have 3 workers and a toolbox, and I need to get them down, and they are not supposed to die in the process. And you have to find the best strategy to do it. It's an optimization problem. You have to do it in the shortest way. There is the code is on my GitHub too if you want to see. So let's go to a deeper dive in some use case. This is the way I log my workout with my phone. I have NFC chips there, and when I work out, I do deadlift, 130 kilos and 3 reps, and it's the way I do. So I can trigger with my NFC enabled phone an event, and I add an event to a chain list. Here I do bench, and I have an automaton to parse this. I can put an iterator on the last event and the current state, and then it can see the next state would be there is no wait anymore because I have changed my exercises, and it has used the transition move, and there is code in this transition that triggers code, and that set a memory to the right values, like move has changed and weights are now empty. I put that in an APOC periodic to reiterate it all, and I can data is not actionable. So what was only some chain of events, I will do it. I will process the data right now. I have an iterator with my state machine and my data, and now I can. Sorry for that. Passwords are sometimes Okay, and now I can see I have reps in my database. I can see all my reps. No, it wasn't. I wanted to show you sets of work. So yeah, I can see I have, for instance, a deadlift set with 3 reps at 150 kilos. So and I can build an app with that in a really straightforward manner. I can see I'm benching this month. Those value 1 rep max was 115 this week. So I have an actionable data from non-structured sequence of events. So thank you. That was what I wanted to show you. And I don't know if there is questions and if we have time for questions.
Sure. Let me just check if we have more questions in the chat window. Just give me a second. Nope, none so far. It was a great session, I believe.
Okay. And I hope I've respected the time. Almost.
Yeah, you're well ahead of time.
How? I'm ahead of okay.
Yeah, we have 3 more minutes.
Okay. So we can play with, for instance, I don't know, Python. There is another language you have not tested. It's the ABC star from the. So it has to start with an A, and then only ABCs. So it's accepted, and if I put a D here, well, it's not accepted anymore. Okay. Well, you can have fun, and I suppose it's also an accepted Python variable. It's the one I use most with foo, bar, and a by d, and playing with my keyboard. And yes, so it's the way I do my. This is the way I do my workout with my phone. NFC chips. You can use NFC chips for a lot of stuff at home. They are really cheap, and you can do fun things. You can put. I put them on toys of my children for their everyday routine to brush their teeth or anything. So it's a nice tool to use for anything. My GitHub repo will be in the slides, and slides will be shared. But my GitHub identifier is my full name. It's Halftermeyer.
Yeah. Would you mind sharing it with me? I can just push it in the chat window.
Okay, of course. There are a lot of windows here. Sorry for
Can you
that.
just push it in the StreamYard window?
Yes, of course. Yeah.
All right, I've got that. Let me just push it. Here you go, John.
Then there is several repos about Automata. And
Super, I think we are right on time. Unfortunately, we don't have any questions from the audience. I believe the session was really exciting.
no problem. Questions welcome later if you have.
Yeah.
This is my email. If you can spell my name, you can send me emails.
That's right.
Yeah.
Thank you. Thanks so much, Pierre.
Thank you,
It
Steve.
was
Thank you,
wonderful
everyone.
having you. Look forward to having you next year as well.
Thank you and goodbye.
Thank
See you
you.
later.
Bye.
See you in next talks.
Yes, as Audrey introduced, I'm going to talk to you about how you can use graph technology to better manage your cloud estate. So I'm going to start in a slightly unusual place by telling you about a king penguin chick. Now these king penguin chicks, if you've watched many wildlife documentaries, you might know that these live in enormous colonies, which are full of lots and lots of different penguins, all making lots of noise and lots of smells all over each other. And when a parent penguin comes back to this colony, they have to decipher that noise, find the right signal in it, and generally speaking, they're quite good at finding their chick. Now, the reason I start with this is because I think it's quite a good analogy for your cloud estate if you run anything of any kind of large complexity. There's lots of consoles, portals, dashboards, alerts, monitoring, logs. There's an awful lot of data and information and noise coming out. But we have this problem of how you find the things you're interested in. For me at the FT and my team, we're interested in surfacing things which can help us use the cloud better. And it can be really difficult to find the problematic things in amongst all this information. And the basic reason for that is that data is not the same thing as knowledge. But I'm speaking at a graph technology conference, so it won't surprise you to know that I'm going to push the point that connected data can give you knowledge. So I'm essentially going to talk about how cloud data plus the twin graph technologies of Neo4j and GraphQL can be turned into knowledge that we can use to manage our estate better. So a little more about me. As Audrey said, I'm Rhys. I'm a principal engineer in the Engineering Insights team at the Financial Times. I've been working there about 8 or 9 years. And for the first 4 years or so, I worked on the ft.com website. Now, this is our flagship product. It's one of the world's leading publishers of news on finance and business. And behind the scenes there are hundreds of microservices run by lots of different teams. We also have a lot of other user-facing products. For instance, here's the Investors Chronicle and our new FT Edit iOS app. And again, there's different teams managing them and lots of different services at play. And again, there's lots of things the end consumer doesn't see. So this is our internal custom-built CMS, which powers our news websites. And again, there's more teams involved and more systems to look after. Now, a picture of that across the entire estate looks a bit like this. Those blue dots are teams, and those orange dots are systems. So across the entire estate, there's lots going on, and there's lots that can go wrong. And 4 years ago, I left ft.com to join the reliability engineering team, which was focused on improving reliability across this massive estate. Now, the initial problem I was tasked with solving is how do we make it quicker to find out who to speak to when something goes wrong? Because when we had outages, quite often it would take longer finding the person who could fix it than it took them to fix it. So we really needed to decrease that time so that outages were recovered from much more quickly. And this is what we came up with to solve it. It's our documentation system. It's called BizOps. And it allows you to search and to browse everything in our tech estate. And you can read more detailed documentation and edit it if you find something wrong. I've spoken about this before, not least at Nodes about 4 years ago. If you're interested in hearing more, then there's lots of links to talks on my website. Now, under the hood, we run this on Neo4j and GraphQL. And the reasons we chose graph technologies is because the relationships between records are incredibly important. So the model which is at the core of this is we have products, which are the things that users interact with. These are powered by systems, and they can have all kinds of dependency relationships between themselves. And they're looked after by teams and by people. So that means when a product breaks, we can follow links through to the systems that underpin it and follow them through to the teams and the people that need to be contacted. And that has really transformed how long things are broken for. It's far easier now for us to speak to the right people quickly. Now, this is what that model looks like applied to just my team. The blue dots are people, the orange dots are the systems we look after, and the yellow dots are the products. But there's kind of a more complete view we could have. This is an alternative model showing all the things our team runs, including all the infrastructure. So that includes all our CDNs, all our data stores, all our compute instances, and lots of other things besides. And there's lots of value in that data, potentially. But if you combine that picture of one team with a picture of an entire department, then you very quickly get to something that looks like this penguin colony, just too much going on, very difficult to pick out the signal from the noise. And our team, for the last year at least, has been really focused on how we turn that massive data into knowledge in order to help us transform the way we run our tech estate. So the first lesson I have to share with you is that it's important to dedicate effort to the problem. So about a year ago, we changed our name from Reliability Engineering to Engineering Insights. It's not just a name change. With that name change, it meant there were lots of problems in the reliability space that we no longer focused on. So we've got more people focused on this set of problems around turning data into knowledge. And that focus has allowed us to really make progress. Alongside that, we've got commitment from our infrastructure management teams to provide us with the raw data. Without us getting hold of data about our infrastructure, we can't turn that into knowledge. So over the last year, we've been adding more and more things to our model of the estate. Most of those contributions are coming from outside our team, and they're as enthusiastic about providing the data as we are about getting it, because they know that providing it to us and combining it with our set of tools can really power some interesting transformations. So there are once we've got the data, there are 4 principles we apply to get the most use out of it. And the first one I'll talk about is keeping your data connected. So what do I mean by connected data? I think the first aspect is that there should be no boundaries between subsets of data. So this could mean if you've got a data set about CDNs and a data set about servers, don't keep them separate. Make sure you're kind of expressing which CDNs are connected to which servers. Similarly, if you've got things owned or run by different departments, don't keep them separate, because if those things interact in the real world, then you're going to want the data about them to interact. An example of where this is delivering value for us is a thing that used to be really hard to manage, was that each AWS account we run has a security scanner in it. And when we need to upgrade that, we'll create a new instance and then go back and clean up the old instance. But we need to do that across 90 accounts. Now, the process to go and check that we have been tidying up after ourselves and cleaning up those old instances was a bit like this. You'd have to log into an account and manually check for old instances, and then you just do that 90 times across 90 accounts. And there's lots of other governance tasks which are similar, where it's just a matter of going in and manually checking lots of accounts. And I have a confession here that was so tedious to do that we weren't doing it effectively. And that caused us to spend a lot of money running instances we no longer needed. And there's potential for security flaws and things like that to crop in because you're running stuff which is out of date. But now we've been able to improve with that using graph technologies. So you can see on the right there, there's a query which is about 10 lines long. Now we have the data about all our accounts in a single graph database. We can just query it in one place. And you can see on the right, we've uncovered that one account has 3 instances in it, another account has 2 instances, and we're able to shut them down and save some money. Another aspect of connectedness, which I think is really important, is that you try and map as many relationships between records as possible, because a rich model with more relationships can give more powerful insights and power more use cases. An example of where we're getting value here is in how we manage our DNS records. We already manage our DNS as infrastructure as code, so we have a big repository full of lots of YAML files that define all our DNS records, all the way from ft.com down to obscure little things that have bits of infrastructure. But we have a problem when it comes to merging changes safely, whether it's ft.com or these little obscure DNS records. We don't really want to open up for anyone to make a change because there's potential to do some real damage to our estate by doing that. But then the team that look after the DNS repository, they don't, other than for a few, such as ft.com, they don't really have the context to be able to successfully review changes to other records. I mean, how could they? There are thousands of domains inside this repository. It'd also be a bottleneck if they were expected to review every pull request. But the graph can help us apply controls in a meaningful way. Here we can see the data we've got in the graph. We've got host records now, and they're connected to infrastructure, which are in turn connected to systems and the teams that are responsible for them. And then reaching out from teams, we've got data mapped to people, and then GitHub teams and GitHub users because we import data from GitHub as well. And what this allows us to do is when a person makes a change to a host, we're able to check, should they be making a change to that host? And we can also add the relevant GitHub team as a reviewer. Now this massively improves the efficiency of review PRs because it's distributed around the department, and improves the quality as well because the people who have the context able to review that change appropriately, they are copied in on it. Now, in order to power that, this is the kind of queries we're talking about. So between two queries, which I'll maybe talk a bit later about how these are glued together under the hood. But we have essentially 9 tables being joined together there, including one recursively. And this is where we really get the value of our choice of Neo4j as a database, because that query can execute really efficiently. We don't really have to worry about tuning that query. In a SQL table, I think you would have to put quite a lot of effort into figuring out how to make that complex query performant. So a second principle of getting value from this data is to keep it open. So I've already spoken about how connected data equals knowledge, but of course you have to have some kind of brain in there, either human brain or possibly AI if you're ambitious, in order to actually create that knowledge. It stands to reason that the more brains you have looking at that data, the more knowledge you're going to have. So opening up access is going to create more knowledge for you. This is probably as good a point as any to talk a little bit about GraphQL. I'm sure most people here by now, halfway through the second day of the conference, know what Neo4j is. But GraphQL is a query and API specification for interacting with graphs of data. And it was developed at Facebook because they had people building user interfaces that had to request data from loads and loads of APIs in parallel. And this was inefficient and difficult to use. So they kind of invented GraphQL as a way of stitching APIs together and creating an interface which was more friendly to interact with. And what Neo4j have done is they've created a library which essentially then converts these GraphQL queries back into Cypher. So essentially, you're able to use GraphQL as a query language for your Neo4j database. But why would we even add that layer? So there are a few reasons. The first one is around safety of execution. If you give people access to write their own Cypher, you give them permission to possibly write dangerous queries which will crash your database. GraphQL, it has lots, at least the implementation that Neo4j have provided, has lots of filters built in, so it's quite powerful. It's not as powerful as Cypher, but it's good enough for most of the needs we come across, and there are ways to extend that. So yeah, it does for us. Also with GraphQL, you already get an API. So we have an API gateway at the Financial Times, and we integrate the API with that. So we already have a way of managing access to it. We don't need to write an API or introduce some processes to manage database users or anything like that. So it takes care of that problem for us. And finally, GraphQL is quite new as a technology, maybe less than 10 years old, but it's really growing in popularity very quickly. And there's a rich ecosystem of tooling around it. So you're providing people who want to interact with the data with something more familiar than saying, go off and learn Neo4j and Cypher. So those are all three very important principles which have enabled us to have a lot of success. So this is what that looks like. We have the Graphical Playground, which is an interface for exploring the data. That's open source. That integrates quite easily with, we use Okta as our single sign-on provider. So that means that anyone in the department can have access. And we have a Slack bot for our API gateway, and users can easily ask for an API key automatically, which will give them access to use the data programmatically. Now, just as a tangent, I will add that because GraphQL comes from a world, its original use case was gluing different APIs together. Even though the implementation we have from Neo4j is about kind of providing a query language for the Neo4j database, you can still stitch it to the other data sources. So if you get other things such as time series or metrics or something like that, that won't really fit in a Neo4j database, but is useful to connect to other sources of data you've got, you can do that. And that means we're opening up access to other sources of data as well, which again increases the pool of connected data and leads to more potential to create knowledge. So the next principle is easiness. So I'm fond of saying to people at the FT when they hear me talk about GraphQL and they kind of go, oh, what's that? Sounds scary. I just say it's as simple as SQL. And it really is. Here are 3 examples of queries in each language, which are all of them getting active people and getting a few properties on each. And other than syntax, they're about the same in terms of number of statements in them and complexity. But GraphQL, I think, is actually a lot simpler than SQL. So if you want to do something more complicated, joining tables, for instance, in SQL, you have to write a join, you have to know which columns include keys and things like that. And Cypher is, I would say, quite a lot easier. It's it's designed to query relationships primarily. But I think GraphQL wins outright here because in the advanced tools you get, there's autocomplete, which is very forgiving. And it's very easy to construct a query, which not only does it ask for the right data, it kind of looks like it's asking for the right data. It's very intuitive. And the tools, they also contain lots of handy stuff like error correction for your typos. Another great thing, I think, is when you query the data, you get data back which looks the same structure. So here we've got a few properties with one nested, and the response data looks exactly the same. Now, to me, this is really powerful because when you're working with graphical data, if you're working with something which just returns rows of data, that to me is a bit jarring, kind of conceptually, when you're trying to manipulate the data. So having something which returns nested graph-like data is really nice. Having said that, we have built a reporting tool which can convert it back into rows of data, because that is sometimes what you want. And this also contains the ability to parameterize queries. Now, we've trained about 100 people on this, mainly engineers, but also some technically minded non-engineers as well, because as I mentioned before, it's no more difficult than SQL, and there's lots of people outside of engineering who have an interest in managing our estate, who would like to be able to work with the data like this. And this has led to some brilliant changes. It used to be the case that our team was reaching out to people, chasing people, asking them to engage with the data and use it. But now we're no longer the middleman. This graph of information and the tools around it have become a medium that teams can use to communicate with each other about the technology we run. And it's really leading to lots of things happening quite quickly. Which takes me on to the next point, which is it's important that your data is fast to interact with. So data-led decision-making is quite an important thing if you want to be a successful business. And typically this means you should have a fast learning cycle. So you can ask a question from the data, get an answer back, and that informs you quick enough that it can inform your next question, and so on and so forth. And you continue in cycles until you found the question that you perhaps need to do something else on. And if you're having to wait days or weeks or even hours to get an answer, this can slow down that process and make it less effective. But what I've described about our stack, hopefully you're convinced that we've built something that allows our users to self-serve answers to questions of arbitrary complexity, and they get instant answers. So that's incredibly good for making sure people are data-led. So that's good, but I think we can do even better. So a question a lot of our teams have is, what should my team be most worried about? Is it security? Is it reliability? Is it costs? And we have lots of data on this. We have like email alerts, Slack alerts, custom dashboards. Most of the tools we use will have alerts or reporting within them as well. So there's lots of data, but as I've said before, this is not the same thing as knowledge. So for the last year, this has been a big focus for us. And what we've come up with is a thing called Problem Hub, which is a set of tools for routing these kind of problems with the estate in the most effective way to target the messages at the right people. So first of all, the first step is to identify a problem. Now, there are two ways of it. There are two ways to get problems in. You can either use our post API or create things manually, just say there's a problem with this thing. But what we're encouraging people to do is to leverage the data we actually have in the graph. So you can see here, there's a query which looks for Heroku apps whose stack is beyond its end of support life. What that returns is a list of Heroku apps which need to be upgraded. So you can send that list of Heroku apps into the API. And then we do insist that people provide remediation advice with these things. So don't tell people something needs upgrading. Tell them what it needs upgrading to and how you do that. And again, the graph information can provide useful context here and can be used to generate more targeted advice depending on the precise case. And finally, this is probably the real strength of Problem Hub, is teams creating problems. They only need to know there's a problem with a thing, because embedded within the Problem Hub API, we have all these queries which use the graph to connect those problems back to the team that is ultimately responsible for it. And this can sometimes be quite long chains of relationships through the graph. So again, that choice of Neo4j as a database really means we can be performant doing that, and we don't need to worry too much about optimizing it. although it's becoming an increasingly popular tool, and traffic is going up and up. So for once, we do the success of it is actually meaning we're having to think a little bit about optimizing things. So now, that question, what should my team be most worried about? The answer to that is your peers using the graph have already told you. So we're not just, so we're really getting ahead of things rather than waiting for people to ask questions and giving a fast response. So here's an example of that in action. We have a bit of a cost-saving drive at the minute, and somebody found that an S3 bucket, which should have contained just a few bytes of data, actually contained terabytes of data because they had misconfigured the logging on it. And they realized, well, this is something that other people could do. It's an easy mistake to make. So within a few hours, we had our team that manages our cloud estate adding these properties and these relationships to our model and adding a few lines to their data importer to write that data to our API. And then we had the data in the graph and we were able to query and see which buckets were logging where. And we shared a message in Slack. We didn't actually get around to adding it to Problem Hub because just providing this information to people via the graph was enough to get people to respond to it. But in general, the common practice now is people will find a problem and they don't necessarily send a message in Slack. You can just kind of instantly go from finding that problem to generalizing it via Problem Hub, and that also broadcasts it to the people who need to know. So that means anything which is wrong with our estate, we can make sure that the people who need to fix it know and also know how important it is compared to other things. And that just about wraps things up. I'll just end by summarizing with a few thoughts. So managing a large cloud estate can be overwhelming, and the amount and variety of data available doesn't necessarily make it easier. But using graph technologies to represent it can help a lot, as well as these 4 practices: keeping your data connected, open, easy, and fast. Thank you. And I did say we're hiring, so do please reach out to me on Twitter, or there's the link for our careers website. Thank you.
Thanks, Sami. Thank you, everyone. Yes, it will be a lightning talk. There'll be a lot to pack in for this session. So I just please ask if we save the questions to the end or to after, and happy to field them through the platform. And as Sami said, I'm going to be walking you through using graph embeddings. So a few of the graph algorithms that were available in Neo4j for my research topic, which was tracing ransomware payments throughout the Bitcoin network. So I hope everyone can see the slides okay. So where did we begin? So a little bit of introductions. Yeah, I only started using Neo4j graphs back in 2018, essentially when I started my journey on my PhD, which is just completed. Thanks, Sami. And the focus, as I said, was on tracing suspicious Bitcoin payments. This was in general at first, and then it sort of narrowed down into actual ransomware payments throughout the Bitcoin ecosystem and the transaction graphs that they formulate. And then, you know, in order to get a bit more of a deeper understanding of the graph and the context of the graph, I started exploring the graph data science library that Neo4j offers. So what did I want to do? Well, the intention of the research was looking at ways of disrupting the ransomware payment networks. As you can see there on the right-hand side, there's quite a dense and sparse graph of a let's say a transaction graph of a ransomware attacker transferring their funds throughout the Bitcoin ecosystem. And I wanted to know about these Bitcoin transactions, you know, how they formed their graph, what patterns they were making. And I needed a visualization tool to help me do that. And Neo4j was something that helped enable that and allowed me to understand the behaviors a bit more better when it came to ransomware payments. But adding to that, just looking at the graphs, you know, analyzing them, as I mentioned, they're quite dense and sparse. I needed to formulate some contextual information out of that. And in order to understand the relative riskiness of such payments with respect to ransomware seed addresses, I needed to look for that contextual information. And the ultimate goal was to try and predict clusters that certain nodes, certain addresses, or certain transactions would belong to. And by doing that, I looked into the graph embedding algorithms available from Neo4j. So where do I start, right? Well, if anyone's familiar with the cryptocurrency ecosystem, you'll know that there's a lot of data, right? And the data that it forms is in natural essence, it's a graph. And modeling this, I was helped greatly through the use of Neo4j, right? It allowed me to take two sides of my problem, which was, you know, how victims are paying in to the collection address that an attacker would control, and then how the attacker then moves those funds beyond the collection of those ransom payments. So I started with a bit of a Python script hack and plugged into a Bitcoin API just to get the data, and then I loaded that into the Neo4j system. Okay, so two graphs essentially, a cache in and a cache out. But, you know, what did that mean? And you can see there in the top right-hand corner, you know, what is the signal within all of this data? You know, the different levels away, so the depth of the graph, the density of the graph, and I needed a way to simplify that model. And as I mentioned before, Neo4j sort of enabled me to do that. It enabled me to embed properties and use those as an enriching feature of my graphs, and essentially, you know, what I could use down the line in my, let's say, machine learning pipeline to further understand the graphs. And this is where the embeddings really proved a bit of a game changer for the research I was doing. There were two embedding algorithms that I looked at. Okay, the first one was the Deepwalk algorithm. And the second one was the GraphSage. I'll first run through the Deepwalk algorithm. So a little bit of background on that. You know, it was made famous in a 2014 paper by Perozzi et al. And they used it against the Zachary's Karate Club graph, which is a very famous sort of data set when using to test embedding algorithms. If anyone's interested, I highly recommend reading that paper to get a deeper understanding of the embedding concept that Deepwalk was looking at. Okay, essentially Deepwalk allowed me to learn structural representations of the graph's nodes, and I could capture the similarity in a whole neighborhood. So one of these graphs, one of the cache out graphs, I particularly focused on, and I was allowed to embed those learnings into the individual nodes within the community of the graph that I was looking at. On the right-hand side, there are a few high-level steps that I went through, and I'd like to share those steps along with some of the code that I used as well. And this is shared afterwards, so please feel free to access the GitHub repo and try and play around with some of this code as well. Okay, so if I step through this flowchart here. So as I said before, so I needed to read in the data into Neo4j. So what did that mean? That means using let's say the APOC load to read in my JSON file. So when I did my data collection, I had a big JSON file which basically formulated the graph that I was interested in. Okay. And with this loading function, I was able to basically set up my data model. So using my addresses as the nodes, the payment transactions as links between those nodes, and then henceforth building the chain of transactions from there. Okay. What was also interesting for me is what I call the depth property. This was also built out of the Python extraction code, and what it allowed me to do was tag each hop, let's say, within the network away from the main seed or collector address that the ransomware attacker was using. So I was interested in, let's say, what happens 4 hops away from that particular address, and then how the transaction graph develops from there. So I could look at any point, any sort of hop away from that address to see what's happening at that level or that depth. This was a very interesting feature for me to use in downstream feature engineering. Some of the other graph data science functions that I was able to use as well were PageRank and community detection. So how did I use them within, hope it's not too small, within the Cypher code and within the graph data science library in Neo4j? Basically, you could call the community detection algorithm that's available within Neo4j, and that would stream out and provide a metric with respect to each of your nodes or transactions within your graph. Okay, PageRank was also used in a similar fashion. Then, with my graph, let's say, set up with the appropriate properties that I wanted to use that for my use case, I was able to then execute the Deepwalk algorithm and then write the embeddings as vectors to those nodes. So quite a simple piece of code there that was allowed to basically run across my graph with the appropriate hyperparameters. And if you do look into the academic paper, there is some explanation around what might be the optimal set of hyperparameters to use with respect to the graph that you'd like to apply this algorithm to. Okay, but these embeddings essentially allowed me now to form some sort of contextual understanding, and the Deepwalk algorithm really does observe each node, right? It takes a random walk from your starting point and then builds this data corpus and reference library, essentially, that you can use to use these embeddings as effectively features for any sort of further machine learning as well. Okay, so that last step there, I had the export to Python to perform some principal components analysis and a k-means clustering. And this was important too. I mean, I used just a Jupyter notebook in order to reduce the embedding dimension down to something a little bit more digestible and something that would be able to be analyzed in a 2D space rather than the whole vector space that Deepwalk uses. Okay. And essentially, that's how I exported it. It's really quite simple within the Cypher in order to get your data set and then really connect that to Python to do a bit more of data science analysis. So that was the Deepwalk approach, right? The next algorithm that I tried. Oh, sorry, before I get to that, actually, what were some of the outcomes of that, actually, which is good to mention. So Deepwalk itself is a transductive algorithm, right? And as I said before, it steps across every node and every aspect of your graph that you would like to perform embeddings on. It operates in more of an unsupervised manner, okay? So versus your standard sort of testing, training, and validation machine learning pipeline. But this is okay. I needed something to basically get a perspective of what might be important and contextually relevant within my graph in a quick and easy fashion, right? And the purpose, as I said at the start, was really to try and find some risk in the nodes within a ransomware payment network. So I was able to use these embeddings that were derived from Deepwalk, push them through the principal components analysis and k-means clustering, but also then use those embeddings, those reduced embeddings in a cosine similarity function that really looked at the risk relative to this ransomware seed address, okay? So stepping out of Neo4j into my Python notebook, I was able to start ranking the riskiness of each of these nodes within my ransomware payment network. But saying that, you know, the Deepwalk algorithm applied to my graph in Neo4j, it's actually not available in the Graph Data Science library. It was actually it's actually in a GitHub, which I have a link to, and you install that separately within your setup for the Neo4j database. And it produced a few, you know, questionable outcomes, I guess. You know, why a higher community risk does not correlate to a higher concentration of risky nodes? Because you can look at them individually, but you can also look at them collectively. Because my objective was to try and disrupt the whole network. Okay, so where's that concentration of risky nodes? But it's not in a very risky community. And if you remember, I used the community detection and the page rank as some indicators of that. Okay. I didn't test any performance or scalability of the algorithm as well, so that's something to take into consideration as a watch point. Conscious of time here, so I'll push through to the usage of the graph sage algorithm. So the graph sage algorithm is actually available in beta within the latest version of the Graph Data Science library, so a lot easier to integrate into your Neo4j database. And the graph sage algorithm differs from the Deepwalk algorithm as it's more an inductive algorithm, right? So in essence, Hamilton et al. Back in 2017 established this for learning on large graphs, okay? So I was able to generalize a function that would try and represent your graph and the node feature information within the neighborhood proximity to generate the node embeddings. I encourage you to take a look at that paper as well. It's very informative in how the algorithm executes and how it's actually implemented within Neo4j. There's a lot of good information in the developer docs. Okay, so again, I read in the data. So the first two steps are fairly similar. Yes,
we are nearly reached the time. Maybe.
Oh, sorry. Okay, I'll really speed through this, right, and just give you some outcomes of what's happened within the output of the graph sage. Okay, again, I stepped through this. There was a few different steps in the process regarding my risk rating element. I actually did the risk rating within the Cypher code. All of this can be shared and accessed through the GitHub repository as well. I used the concept of the graph catalog, which is a very powerful component of Neo4j, and it allows you to use this multiple times within your analytical workflow. Okay, so that was another benefit of using Graph Sage, and it was more executed in a supervised fashion, right? So you'd have your traditional testing, training, testing, and validation data sets. And what it revealed is some different types of graphs within my overall graph. And it allowed me to do a lot more, let's say, specific feature engineering, okay? Which helped me, in essence, achieve my objective of trying to predict where a node, an address or a transaction may belong as a part of a cluster, okay? So I broke down these three graphs into small transaction clusters, seed transaction clusters, and large transaction clusters. So some key takeaways, and of course, please feel free to connect with me on LinkedIn and ask me questions after this presentation. But looking at the graph embedding frameworks for Neo4j, they really give you the opportunity to provide rich context for complex graph understanding, which is what I needed for my research, okay? You can build feature stores and enrich your graph with knowledge, okay? This is another great benefit of using the Neo4j platform and the Graph Data